Okay, we're going to take a look at these 3 free response questions that went with chapters 3 and 4 here. Again, you can check out the rubrics that I gave you if you want to look at things in a little bit more detail, but sometimes it's helpful just to kind of talk through an example that I sort of have worked out here. So in this first one, this was talking about the Great Plains Railroad, and they're interested in studying how fuel consumption is related to the number of rail cars for its trains on a certain route between Oklahoma City and Omaha. So obviously, the more rail cars that a train might be pulling, the more fuel that it's probably going to have to use, because that's just heavier to kind of pull across the tracks there. So we have a random sample of 10 trains here that you're given. Okay, this left column, which is going to be our X values, that's the number of rail cars that the train is pulling, and then our Y variable is the fuel consumption. So like how much fuel is that train having to consume in the number of units per mile. So units would be like, with gasoline, it's gallons per mile. So whatever this is for the train, like a train that's pulling, this train that's pulling 20 rail cars, they had to use 58 units of fuel per mile that they were pulling that train. Okay. Other information they give you here, you can see they give us a scatter plot of that data, and then over here they give us a residual plot, which will be helpful with one of the questions they're asking us. And then it's been a little while since we've looked at computer output, but we definitely want to be comfortable with identifying certain pieces to this computer output. Okay, namely, right up here, they're giving you the regression equation. Okay, and the rail car is your X variable, and right underneath here, that's your slope. Okay, so this is our slope. And then right across from the constant here, which is this part, okay, that is the y-intercept. Okay, so we'll come back and take a look at that. Let's look at the first question here. It says, is the linear model appropriate for modeling data? That means like for making predictions and things like that. Is a linear model appropriate for this data? It's asking us to clearly explain our reasoning. Okay, now the answer is yes, a linear model is appropriate, and you could have said one of two things. Okay, I like this way the best. One reason is if you look at the residual plot, that residual plot should show absolutely no evident pattern. So let's just go back real quick, take a quick peek. The residual plot is this one over here on the right. We can see that there's some points above, there's some points below, but it doesn't feel like this residual plot is any evident pattern. That's always an indication that doing a linear regression to then make predictions from would be completely appropriate. The other thing that the rubric said would be acceptable for you to say that a linear model is appropriate would also have been to simply say that the scatter plot appeared to be approximately linear. Okay. The reason I don't like that as much is because sometimes your scatter plot can look linear, but you shouldn't run a regression. And just a quick example of that would be if your graph was a parabola, but your scatter plot was just a very zoomed in portion on that parabola, so zoomed in that maybe those points sort of felt like they were linear, but they really weren't. It was just zoomed in really close on the parabola. That would have been very evident. The residual plot would have been able to recognize that pattern there. Okay, so that's what part A is. Part B, I just think this is worded in a really confusing way. It really isn't wanting you to do anything overly complicated, but just the phrasing of this, I could see how people could get tripped up on this. This was asking for us to assume that the cost for a unit of fuel is $25, okay? And then they're wanting us to give a point estimate for how the change in the average cost of fuel per mile would be affected for each additional rail car that's attached to the train. Okay, now remember, average is kind of, when we talk about lines, that's really talking about the slope. Okay, now what you see that I have written down here is this is just our regression equation, and I got that from this computer output. I actually didn't even have to piece it together because they gave that to us right here kind of already put together. Okay, you'll notice I put one of those little hat symbols right above this because that's for predicted fuel consumption. Okay, but average cost of fuel per mile is slope. Okay, slope is always the change in y per the change in x. Okay, y is the fuel consumption and x is the rail car. So our slope on this is representing how much fuel is being consumed per rail car. Okay, here's our slope. That's this number here, 2.1495. So it's using, each rail car on average is using up about 2.149 units of fuel. The question is, if the fuel costs $25 per unit, then on average, how much is each rail car costing? Okay, so then I simply wrote out, well, if each unit of fuel is $25, then I'm going to multiply, this is how much on average units of fuel are used per rail car, so I'm going to multiply these together, and I get $53.74 is how much each rail car costs on average. Okay, part C, it wants us to interpret the value of r squared in the context of this problem. R squared is what we call the coefficient of determination that can be found in the computer output right here. Okay, and this is a template that we just kind of have to memorize. This is something you probably want to go back and study here. This should be on your nuts and bolts. We're saying that 96.7% of the fluctuation or variation in the fuel consumption is accounted for by the linear relationship with the number of rail cars. So it's telling you how much the number of rail cars are impacting how the fuel consumption is varying. And finally on this one, it says, would it be reasonable to use the fitted regression equation to predict the fuel consumption for a train on this route if the train had 65 rail cars? So what you want to do is you want to look back at the original set of data and take a look at how those x values spanned. And you'll notice when you look at those, I think the smallest number of rail cars was 20, and it went maybe up to like about 50 right here. Okay, we did not have any values in our data set that were as high as 65. And this would be an example of extrapolation if we were to make a prediction for rail cars that high. So we're saying no, that would not be appropriate. It would be extrapolation. It potentially could be an unreasonable prediction if we were to use that with our regression line. Okay, all right, let's go ahead and take a look at the next one. This next one is all about designing experiments, and these are where you're really finding yourself having to sort of write out a lot of details so someone could kind of pick your plan up that you had listed and kind of follow through with the plan that you've created. And so this is mentioning that we have high cholesterol levels in people typically can be reduced one of two ways. It can be reduced through exercise, or it can be reduced by taking a drug. Okay, so we have this pharmaceutical company and they have a new cholesterol reducing drug. Now let's read this carefully. The researchers look at what they want to compare. They're not comparing exercise. They want to compare the effects to the effects of the cholesterol reducing drug that's currently available. Okay, so our two treatment groups are the new drug compared to the current drug, okay, or the old drug here. Okay, they had volunteers who had a very high history of high cholesterol, who are currently not on medication. They were recruited for this study. Okay, the first part to this says explain how you would carry out a completely randomized experiment for the study. So you need to detail what are your two treatments, how are you going to take these volunteers and randomly assign them. You can see here I said the two treatment groups would be created. One's going to receive the new cholesterol reducing drug, the other will receive the current, and here's where we start mapping out the plan. You can do this a variety of ways. I chose a coin. I said the volunteers are going to flip a coin. If they get heads, they're going to go to the new medicine treatment group. If they get tails, they're going to the current medicine group. You could say put everybody's name in a hat, and the first half of the slips of paper that I pull out, they're going to go to the new medicine treatment group, and all the remaining ones will go to the other. You could use a random number generator. The idea is you have to spell out in detail what the procedure is going to look like. Okay, and then once it says here, after a period of time, the two groups then would compare their cholesterol levels. Okay, so that would be a completely randomized experiment. Okay, now it says describe how an experimental design could be improved if we incorporated blocking. Now remember back at the beginning, it mentions that people that exercise, that could reduce your cholesterol level somewhat. Okay, so what we might want to block by is we might want to split the group into one group who exercises and one who doesn't. Okay, and these don't have to be equal groups. We're not doing this randomly. We're not flipping coins. We're saying, look, if you exercise, go to this side of the room. If you don't, go to this side. And then here's the key. Within each block, then we're going to randomly split them into treatment groups. Again, with the coin, I said heads new medicine, tails current medicine, and then you want to address how blocking is beneficial. And I said this blocking allows for us to control for the confounding variable of exercise. We can compare those who exercise and take the new drug with those who exercise and take the current drug. Same thing with those who don't exercise. Okay. And finally, it says, can the experiment be carried out in a double-blind manner? And you can read what I have there. Yeah, they can. The people can take a pill and not know which drug it is, and the doctor analyzing their cholesterol levels doesn't have to know what treatment group they were in. Okay. Okay, our last one here, we may have done this one before. Talking about an apartment that has 9 floors to it. Each floor has 4 apartments on it. The building owner is wanting to install some new carpet, and they're wanting to install carpet in 8 of the apartments to see but they want to see how well it's going to wear before they replace it in the entire building. So they're just going to sample 8 apartments first. The figure below shows you all the floors, and you'll notice it says here, if there's a little asterisk next to the number, that is an apartment that has children in it. Okay, so it says, for convenience, the apartment building owner wants to use a cluster sampling method in which floors are the clusters to select the 8 apartments. Describe a process for randomly selecting 8 different apartments using this method. When you do cluster sampling, that's when you are selecting like an entire group. You select the group at random, but then everybody in that group is going to be in your sample. And so I said use a random number generator on the calculator. I want to generate 2 random numbers between 1 and 9 because there are 9 floors. Okay, I'm going to exclude any repeats or any numbers outside of the range, and then I'm going to sample each of the 2 floors selected for every apartment to get the new carpet. Okay. Okay, now on the next part here, it says there's an alternative method, and this method, though, would require stratified random sample. But we still want to sample 8 apartments, but the difference here is a stratified random sample of size 8. We're going to pick 2 random apartments that have children and 6 random apartments that have no children in them. It says, in the context of this situation, give 1 statistical advantage, okay, of selecting such a stratified sample opposed to the cluster sample. Okay, so if you look back, you'll notice that there were 3 floors that had no children on them at all. Okay, these right here are the 3 floors that had no children. And so we could say, since 3 of them had no children, if we did the cluster method, it's possible that the 2 floors that we would randomly pick could have come from any of those 3 floors with no children. And then we want to kind of address, what's the big deal with the children? Well, children could cause the carpet to wear out more easily. They could spill things accidentally. So it's nice to have a sample that has some apartments with the children. And this is why a stratified sampling method is a little more advantageous, because here's why statistically. It allows for the proportion of apartments with children in it to remain the same proportion for your sample. Okay. For example, if you look back at the picture, in the population, the entire building, 9 of the 36 floors had apartments with children, and in the sample, it was suggesting that 2 of the 8, we would pick randomly 2 out of the 8 to have apartments with children. So we're keeping that consistent, so it's in line with what we are seeing with the population. That's why that's kind of a better way to go with this. Okay, if you guys have questions, please reach out to me. I will talk to you soon.